The ecological niche of an organism is the position it fills in its environment, comprising the conditions under which it is found, the resources it utilizes, and the time it occurs there. Habitat. The habitat of an organism is the physical environment it is found in, for example, a temperate broad-leaved woodland. Each habitat provides numerous niches. Multidimensional. Each condition or resource which defines the niche of an organism contributes the space one dimension to the space in which the organism can occur. Considering all dimensions together defines fully the organism's niche, and is the multidimensional niche space, or n-dimensional hypervolume. Fundamental niche. The niche space an organism can fill in the absence of competition or predation is known as the fundamental niche. Realized niche. The niche space occupied by an organism when competition and predation occur is the realized niche, which is always a subset of the fundamental niche. Related topics. The nature of competition. 11. Resource partitioning. 13. Intraspecific competition. 12. Niche organisms of a given species can maintain viable populations only under a certain range of conditions, and will utilize only particular resources. They also may only occur in a given environment during particular times, e.g. insectivorous bats are nocturnal, when few insectivorous birds are feeding. The intersection of these factors describes the niche, which is the position the organism fills in its environment. Organisms may change niches as they develop. For example, common toads bufo occupy an aquatic environment, and are grazers of algae and detritus prior to metamorphosing into adults, whence they become terrestrial and are insectivorous. Habitat. In contrast to the niche of an organism, a habitat is the physical environment in which an organism is found. Habitats typically contain many niches and support many different species. Thus, temperate broad-leaved woodland provides a vast number of niches for a range of birds, e.g. nuthatches, great tits, woodcocks, mammals, e.g. wood mice, foxes, common shrews, insects, e.g. butterflies, moths, beetles, spiders, aphids, and plants, e.g. wood anemones, bluebells, mosses, lichens. B3 The niche. 19. Multidimensional niche space. Each condition that affects an organism or resource that it utilizes can be regarded as a single axis or dimension within which there can be defined a range that the organism will occur in. By considering a number of such dimensions at once, an increasingly refined picture of the organism's niche can be reached. For example, the temperature range which a chaffinch will tolerate will overlap with that of many other species. However, if we consider the prey size and the foraging height as further dimensions, we will differentiate the chaffinch niche from that of many other species. Figure 1. In Fig. 2, the niche of an American warbler, the blue-gray gnatcatcher, is shown in 2 dimensions. It is theoretically possible, though difficult to measure or represent on a page, to add every dimension of resource or condition which affects the organism, resulting in a fully defined ecological niche, the W-dimensional hypervolume, where n is the number of axes. Simple theory suggests that this fully defined niche is expected to be unique to that one species, or even one life stage of that species, although recent work shows this need not be so in a dynamic or patchy environment. See topic 13. A practical weakness in the n-dimensional hypervolume theory is that it is impossible to be sure that all dimensions have been considered, but, nevertheless, this is a useful concept. B. Temperature. Temperature. Figure 1. Niche dimensions for an insectivorous bird. A 1-dimensional niche covering temperature tolerance. B a 2-dimensional niche incorporating temperature and prey size. C a 3-dimensional niche incorporating temperature, prey size, and the height at which foraging occurs. Prey length. Figure 2. The feeding niche of the blue-gray gnatcatcher based on prey size and feeding height in Californian oak woodlands. Contours represent feeding frequencies. Redrawn from Ecology and Field Biology, 5th edn. R. L. Smith, 1996, Addison Wesley Longman. 20 Section 8 Adaptation to the environment. Fundamental niche. Realized niche. The niche space a species can occupy is affected by the degree of competition and predation that impact upon it. Commonly, in the absence of these stresses, a species can thrive in a wider range of resource levels and conditions. This potential niche space is the fundamental niche. Normally, species are exposed to competitors and predators and are hence limited to a more restricted niche space, known as the realized niche. The impact of competition on the fundamental niche is illustrated by a classical experiment on 2 species of Gallium spp. By the plant ecologist Tansley. Heath bedstraw Gallium saxatile is found on acidic soils, whilst slender bedstraw G. pumilium is found on calcareous soil. When grown alone, both species thrive in both soil types. However, when the species were grown together, slender bedstraw was excluded on the acidic soil, whilst heath bedstraw was excluded from calcareous soil. Clearly, competition affects the observed niche. Experiments with guppies Picilia reticulata and sticklebacks Gastrosteus aculeatus suggest that the proximity of a predator constrains the fish to feed in sheltered areas where predation risk is lowered. In another example, the pattern-off feeding times of the 3 American bat species shown in Figure 3 suggests that the realized temporal niche of these animals is also shaped by interspecific interactions. Hours after sunset. Figure 3. Foraging activities of bats in Iowa woodlands. Dotted line, brown bat, solid line, silver-haired bat, dashed line, hoary bat. It may be noted that mutualists also affect the realized niche of an organism, but in contrast to predators and competitors, the presence of a mutualist will tend to expand the realized niche rather than contract it. In the more extreme cases of obligate mutualism, such as that between many orchid species and their fungal mycorrhizal root mutualists, the niche of the single species may be non-existent. Orchids without their mycorrhizae simply do not grow. Niche theory is explored in more depth in Section I. Section C. Climate. C1 SOLARRADIATIONAND. Climate. Keynotes. SOHR radiation. Global wind. Patterns. The circulation of oceans. Rain. Solar energy drives climatic processes. Energy from the sun strikes the earth where high energy wavelengths of light are absorbed and re-emitted in the form of radiant heat. Warmed air rises and expands as it does so. This expansion takes energy from the air, resulting in temperature reduction, a process known as adiabatic cooling. The major wind systems of the Earth result from the upward movement of warm air around the equator, which is replaced by cooler air coming from the north and south, forming the trade winds. The Coriolis effect caused by the Earth's rotation deflects moving air to the right in the northern hemisphere and to the left in the southern hemisphere. The trade winds meet just to the north of the equator in the Intertropical Convergence Zone (ITCZ). At 40 degrees north and southwesterly, upper atmosphere jet stream winds occur. Ice packs at the poles increase the surface reflectance, or albedo, which reduces the heating of the air, resulting in zones of dense cold air. The world's oceans are stirred by winds. Trade winds pile up water against continents, causing an imbalance in sea levels. For example, in North America sea levels are 1 or 2 meters higher on the Atlantic side than the Pacific side. This difference drives oceanic currents. Thus, for instance, warm water piled up in the Caribbean moves northwards along the American coast as the Gulf Stream and then veers towards northern Europe, where it provides a strong warming influence. Rain falls when moist air cools. Warm air can hold more water than cool air, so cooling causes water droplets to condense and fall as rain. If, for example, air travels over sea and then rises over a mountain, the air will cool at the adiabatic lapse rate, which is 6-10 degrees Celsius km1, depending on water content, and rainfall will result. After crossing the mountains, the air will descend and warm as it is compressed, leading to a rain shadow on the lee side of a mountain. Static conditions in tropical oceans can lead to storms. Minimal movement of air over warm water over a period of days can be disrupted by columns of warm air suddenly rising, resulting in surface winds being sucked into the rising column. The rising air is saturated with water, and as it rises the air expands and cools. The water vapor turns into droplets, which release their heat of condensation and provide energy to further fuel the process, which may develop into a hurricane. Related topics: Microclimate, C2, Ecosystem Patterns, SI. 22 Section Euroclimate. Solar radiation. The Earth is a rotating sphere which orbits the Sun. The equator lies just a few degrees away from being parallel with the plane of the Earth's orbit. Figure 1. This means that the irradiance per unit area is always greater at the equator than it is at high latitudes. High latitudes therefore receive less heat than low latitudes. It is this inequality in energy supply that drives the Earth's climate and therefore determines the distribution of organisms over the Earth. The plane of the Earth's rotation is 23 degrees 27 feet from being parallel with the plane of the orbit. It is this angle that is responsible for seasonality in the northern and southern hemispheres. The variations in solar radiation from summer solstice to winter solstice at 3 locations, a temperate region, a tropical region and a high latitude region, are shown in Figure 2a. A second inequality is the distribution of night and day. All areas of the Earth have exactly the same amount of night and day each year. However, while at the equator night and day come in 12-hour cycles, at the poles day and night. Northern summer, northern winter. B. 77. Figure 1. Relative positions of the Earth and Sun at summer and winter solstice. The plane of the Earth's rotation is 23 degrees 27, from being parallel with the plane of the orbit. From Ecology 2, P. Collinvo, 1993. Reprinted with permission from John Wiley & Sons, Inc. A. Temperate region. T3. Tropical region, high latitude. Month. B. June 22nd. A. Dec. 22. Hour. June the 22nd of December. 22. AA hour. O55 Company G. June the 22nd. C1 Solar radiation and climate 23. Global wind patterns. 8 o'clock. 7:30, 7 o'clock. E6:30 Q. At 6 o'clock EF 5:30. 5 o'clock 4:30, 4 o'clock. Figure 3. Seasonal variation in the time of day when flying squirrels become active. Redrawn from Elements of Ecology, 4th edn, R. L. Smith and T. L. Smith, 1998, Benjamin Cummings Publishing. Come in 6-month cycles. These diurnal variations can be seen in Figure 2b. These changes in seasonal rhythms of night and day have a major effect on animal behavior. The flying squirrel, for example, starts its daily activity with nightfall, regardless of the season. As the short days of winter turn to the longer days of spring, the squirrel begins its activity a little later each day. Fig. 3. The result of these variations is a more constant heat at low latitudes. Low latitudes are therefore always warmer than polar regions. This results in the mass transfer of heat from the equator to the poles in the flow of air and water. A major part of this heat transfer is by ocean currents, due to the high specific heat capacity of water. However, movements in air are more rapid, giving rise to the properties of climate. Energy from sunlight strikes the Earth where the high energy wavelengths of light are absorbed and re-emitted in the form of radiant heat. The primary heating of the atmosphere comes, therefore, from the ground and ocean surfaces. The warm air rises and as it does so the air expands and cools. The cooling of the rising air as it expands results from the expenditure of energy by the warm air during expansion. This process is called adiabatic cooling. The cooling is a function of altitude and the adiabatic lapse rate in dry air is approximately 10 degrees Celsius per 1,000 meters of elevation. In moist air the lapse rate is less because heat is gained as water condenses, falling to approximately 6 degrees Celsius per 1,000 m. The major wind systems of the Earth result from the fact that masses of air around the equator are forced to rise by ground heating, causing cooler air to move in from higher latitudes, which in turn is replaced by descending air to fill the void. However, this simple system is modified by the Coriolis effect, see below, and the properties of scale, resulting in the patterns shown in Figure 4. The revolution of the Earth causes winds to be dragged by the surface, thus deflecting their courses. An object at the equator revolves at a speed of approximately 1,500 kilometers h_1. At higher latitudes, the object would be moving more slowly as the distance traveled for one revolution of the Earth is less. Any mass of air moving away from the equator has an initial velocity of 1,500 kilometers h_1, and as the air travels into areas where the surface moves more slowly, it veers in the direction of its superior momentum. This diversion of winds through their own angular momentum is called the Coriolis effect, named after 24 Section C climate. The circulation of oceans. N. Year 4. Winds at sea level. The doldrums at the Intertropical Convergence Zone ITCZ are shown at the geographical equator as they would be on an ideal Earth. From Ecology 2, P. Collinbeau, 1993. A 17th century French mathematician. Southward traveling air in the northern hemisphere will be deflected to the right, just as northward traveling air. In the southern hemisphere the directions are reversed, with deflection to the left. At tropical latitudes, the surface air that fills the equatorial void from the north is deflected to the right and becomes the northeast trade wind. Close to the equator it meets air coming from the south that was deflected left, the southeast trade wind. Because there is less land to slow the air in the southern hemisphere, the trade winds do not meet at the geographical equator, but instead converge at the Intertropical Convergence Zone ITCZ north of the equator. Heated air rises rapidly along the ITCZ leading to heavy rains typical of Caribbean islands. At latitudes higher than 30 degrees, the sinking of upper air forces winds from 30 degrees to 40 degrees latitude to set off poleward. However, they are directed to the right in the northern hemisphere and to the left in the southern hemisphere by the Coriolis effect. This results in westerly winds in both hemispheres at about 40 degrees latitude. In the southern hemisphere, latitude 40 degrees has virtually no land to slow the winds, resulting in the roaring 40s, winds of high velocity which track the 40th parallel. Upper atmosphere winds along both 40th parallels are also westerlies, the jet streams. Because atmospheric pressure is higher at low latitudes, upper air flows poleward to where pressure is lower. Coriolis effects divert the wind eastward in both hemispheres leading to westerly jet streams. At the poles the lack of irradiance has severe consequences for climate. One pole is covered by floating ice packs while the other is covered by glacial ice. The ice acts as a reflecting mirror, increasing the albedo reflectivity and reducing the heating of the air. Dense, cold air therefore sits over the poles, flowing out into subpolar regions as the cold east winds of northern Europe. The world's oceans are also stirred by the winds. The drive provided by the trade winds pushes masses of water up against continental dikes downwind. CL solar radiation and climate 25. Rain. For example, the North Atlantic Ocean begins as water piled up in the shallow Caribbean Sea, being heated by the tropical sun. This piling up of water by the northeast trades means that the sea level is 1 or 2 meters higher on the Atlantic side than the Pacific side. The water piles up in the Caribbean and escapes northward along the American coast as the Gulf Stream. However, moving water is also affected by the Coriolis effect, and the Gulf Stream veers right towards northern Europe and warms the British Isles, which accordingly has a much warmer climate than places in Canada well to the south of it. The Gulf Stream continues to veer right until the trade winds once again take control. In the southern hemisphere, ocean currents rotate in the opposite direction, counterclockwise. This is most clearly demonstrated by the way ocean currents follow the roaring 40s in a perpetual cycling of the globe. As currents turn back towards the equator, they move along the lee of a continent. For example, in the North Pacific the warm current flowing north and veering right is the Japan current which bathes southern Alaska and British Columbia with water which may be warmer than the adjacent land. These coasts therefore have fog. But then the ocean currents veer right again and travel down the coast of California, where the Coriolis effect turns them away from the coast and out to sea. What happens then is that colder water must be taken from below the surface to replace this water. Cold bottom water surfacing in this way is called an upwelling, and these are areas of high biomass productivity due to the presence of nutrients brought to the surface. Rain falls when moist air cools. This will happen when high irradiance of the sea along the ITCZ raises moist air to great heights, resulting in condensation, then rain. Rain also falls when winds are deflected by mountain ranges. Figure 5 shows the progress of events. Air arriving from the sea rises up a mountain, Q. ECDCN. Cools before condensation. Condensation level cooling takes place saturated once. Descent commences and therefore warms. Figure 5. Precipitation along mountain ranges. The rain shadow. (26 Section C climate. Havoc. Cooling as it goes with the adiabatic lapse rate, 6-10 degrees Celsius km1, depending on water content until water condenses. Rain forms high against the mountainside. The air continues to rise, but now cools only at the adiabatic lapse rate of 6 degrees Celsius km1. The air crosses the mountains and begins to descend. The descending air warms as it is compressed 10 degrees Celsius km1 while also taking up moisture, giving rise to a rain shadow on the lee side of a mountain. Descending air will always absorb moisture. Therefore at 30 degrees latitude, where the air is sinking, the area will always be dry. Major deserts such as the Sahara, the Grand Gobi and the American Southwest lie in this belt. Rising air is required for rain. However, air can be prevented from rising over large geographic regions by a process called inversion. An inversion is warm air floating over cold, forming a stable relationship. The commonest form of inversion results when winds blow across cold ocean water, cooling the air at the bottom. The cold winds blow on in. Because of the low temperature and surface wind, the winds are dry. The Galapagos Islands are desert due to inversion even though they are located at the equator. The hot air rising from the heated Galapagos Islands causes a thin layer of stratus to form at the inversion. The most complete deserts are on the western coasts of continents, such as northern Chile, where cold upwellings along the shore cause inversions. Water piled up in the tropical seas, such as the Caribbean, by the trade winds can be heated throughout by the sun. If there is minimal lateral movement of air and water for a critical number of days, then columns of air can rise suddenly over the warm sea, causing surface winds to be sucked in to feed the rising column. However, the rising air is saturated with water, and as it rises the air expands and cools. The water vapor turns into droplets, releasing their heat of condensation high above the surface of the sea. Now the rising column is heated from near the top as well as from the bottom. To supply the rising warm air, yet more air is sucked up at the surface. The surface winds angle in due to Coriolis effects, and the whole structure begins to spin. This vortex is now called a hurricane. Once over land, the hurricane loses its source of warm, moist air and will eventually collapse. However, the air in the hurricane continues to rise, expand and cool, and rain falls. Surface air also strikes at speeds in excess of 100 miles h1, causing devastation. Section C. Climate. C2MICROCLIMATE. Keynotes. Local variations. In climate. Heel. Temperature. Relative humidity. Global maps of temperature and rain obscure local variation. However, on an even smaller scale there is a great deal of microclimatic variation. The microclimate is the climate in which plants and animals live. A major storage location for heat in temperate ecosystems is the soil, which acts as a sink during the day and a source at night. Thermal conductivity, a measure of the standardized rate of heat flow of soils, determines the rate of heat transfer. The temperature change that a body experiences as a result of the heat transfer will vary with its heat capacity. The heat capacity of a substance is the amount of heat required to raise 1 cc by 1 degree Celsius. Temperature profiles develop in the air above the ground. During the night, ground and crop surfaces cool rapidly so that the surface becomes the coldest location in the profile. Thus, a temperature inversion develops in which air temperature increases with elevation. During the day, the surface is the warmest location in the profile, and under these conditions air temperature decreases with elevation. Relative humidity is the air-water vapor content expressed as a ratio to the saturated water content at that water temperature. Water vapor is derived from the evaporating surfaces of land, water and vegetation. Microclimate variations in relative humidity can be even more marked than those involving temperature. The transport of water vapor is usually upward during the day. Related topics: solar radiation and climate, CL, ecosystem patterns, SI. Local variations. Global maps of temperature, winds and rain hide a great deal of variation at the in climate local level. However, even on a smaller scale there is a great deal of microclimatic variation. For example, the sinking of dense, cold air into the bottom of a valley at night can reduce the air temperature by some 30 degrees Celsius below the air temperature 100 meters above the valley. On a yet smaller scale, air in the immediate vicinity of a low alpine plant may be 20 degrees Celsius higher than air only 0.3 meters above the plant. Hence, we must not merely confine our attention to global or geographic patterns when examining the influence of temperatures on the distribution and abundance of organisms. The microclimate is the climate in which plants and animals live, and is scaled to the organism in that the microclimate of a tree is different in scale to the microclimate of beetle larvae in soil. Microclimate differs from the climate which prevails above the first few meters over the ground, primarily in the intensity of the changes with elevation and the changes with time that occur there. Heat. Soil constitutes a major storage location for heat, acting as a sink for energy during the day and a source to the surface at night. The flux of heat in and 28. Section C. Climate. Out of the soil is a process of thermal conductivity. Thermal conductivity in soil depends upon porosity, moisture content and organic matter content. It is defined as the quantity of heat flowing in unit time through a 1 square centimeter cross-section of soil in response to a temperature gradient of 1 degree Celsius cm1 of depth. The thermal conductivity of soils determines the rate of heat transfer. The temperature change that a body experiences as a result of the heat transfer will vary with its heat capacity. The heat capacity of a substance is the amount of heat required to raise 1 cc by 1 degree Celsius. Heat is continually moving into or out of the soil, and the thermal energy is being continually redistributed in the soil. In addition, the pattern of soil temperature profiles changes rapidly during a normal day. Figure 1. The soil surface is coldest in the early morning and warmest in the early afternoon. The amplitude of the daily soil temperature variation decreases with depth into the soil. At midday, heat is directed downward through the upper 100 centimeters of soil. Heat exit from the soil begins after sunset, but some heat flow continues downward throughout the night. During the summer there is a net daily gain of heat in the soil. Figure 2 shows the temperature variation of an Arctic plant Novosibirsk glacialis on a sunny day. A. €2 Microclimate 29. Temperature profiles. Relative humidity. Figure 2. Temperature variations in the Arctic plant Novosibirsk glacialis on a sunny day with an air temperature of 11.7 degrees Celsius. Redrawn from Elements of Ecology, 4th edn, R. L. Smith and T. L. Smith, 1998, Benjamin Cummings Publishing. Temperature profiles also develop in the air above the ground as well as in the soil. During the night the surfaces of both the ground and crops cool quickly so that the surface becomes the coldest location in the profile. Fig. 3. Air in contact with the surface loses energy to the surface, becoming chilled and heavy. Thus a temperature inversion develops in which air temperature increases with elevation. During the day the surface is the warmest location in the profile, and under these conditions air temperature decreases with elevation. Temperature profiles extended down into plant canopies differ from those in free air. Differences in shading and air movement occur, resulting in changed air temperature profiles. The same variations in temperature are also caused by depth in water or soil. Depth has two effects on fluctuations of temperature. Firstly, the fluctuations are diminished or damped, and secondly, they lag behind the fluctuations at the surface. The strength of these effects increases with depth and decreases with thermal conductivity of the medium, low in soil, higher in water. Relative humidity is the ratio of actual to saturation water vapor. Water vapor is derived from the evaporating surfaces of land and water. The transport of water vapor into and through the layer of air adjacent to the ground is analogous to heat transport. Microclimate variations in relative humidity can be even more marked than those involving temperature. The transport of water vapor is usually upward during the day. It is not unusual, for example, for the relative humidity to be almost 100%, i.e. saturated, at ground level amongst dense vegetation, while the air immediately above the vegetation less than 0.5 meters away has a relative humidity of only 50%. However, the shape of the relative humidity of the air profile may vary throughout the day. At dawn, the 30 section C climate. Time of day. Figure 3. The pattern of air temperature at 1 meter solid line and 16 meters dotted line above a soil. Relative humidity may be constant with elevation. As the day progresses, evaporation at the surface increases the relative humidity of air at the surface, but by early evening evaporation decreases and the relative humidity of the air is lowered at the surface. Section D. Water. D1THEPROPERTIESOFWATER. Keynotes. Water is the universal internal medium of all organisms, comprising more than 90% of living matter. The shape of the water molecule, with an Ho angle of 105 degrees, results in the side with the hydrogen being positively charged electropositive, whereas the other side is negatively charged electronegative. This explains many of water's properties relative to physical and chemical reactions. It also explains why water is attracted to charged ions. The penetration of visible light through water bodies follows a negative exponential relationship called Beer's law. Since water strongly absorbs infrared radiation, that portion of the solar spectrum will be sharply depleted as water depth increases. Furthermore, turbidity due to suspended solids, silt, will strongly deplete visible light. Two features of water make it particularly suitable as a medium for life forms to inhabit. Water has IA high heat capacity and E maximal density at 4 degrees Celsius. A high heat capacity means that it can absorb heat energy with only a small increase in temperature. As a result, aquatic life forms are buffered from temperature fluctuations. Water becomes increasingly dense and therefore heavier at lower temperatures, with the maximum density occurring at 4 degrees Celsius. Thus, ice floats on water and a body of water freezes from the top down. This phenomenon protects aquatic organisms because ice acts as an insulator to prevent further decreases in temperature in the underlying water. At terrestrial temperatures, water passes easily from vapor to liquid and solid phases with a large release or absorption of heat. For example, the evaporation of 1 gram of water requires about 2,430 J of heat, the latent heat of vaporization. The vapor is carried in air until the water condenses, releasing 2,430 Jg_1. When water freezes, about 335 Jg1 is released as the heat of fusion, and the same amount of energy is required to melt the snow. Thus, these energy-consuming and releasing processes in water phase changes provide the mechanisms for the transportation of large quantities of heat to and from the surface of the Earth. Related topics: plants and water D2, animals and water D3. Energy transfer in water phases. Water and temperature. Penetration of light through water. Chemical properties of water. Chemical water is the only inorganic liquid that occurs naturally on Earth. It is also the properties of only chemical compound that occurs naturally in all three physical states: solid, water, liquid, and vapor. Water existed on the planet long before any form of life evolved, but since life developed in water, it is the universal internal medium of all organisms. Living matter is made up of more than 90% water. Water is also the external medium of all aquatic life forms and can function as a resource, condition, and a habitat. The unique relationship between water and living. 32 Section B. Water. Penetration of light through water. Water and temperature, energy transfer in water. Phases. Organism stems from the fact that water is a universal solvent. Almost anything will dissolve in water to some degree. The shape of the water molecule, with an Ho angle of 105 degrees, results in the side with the hydrogen being positively charged, electropositive, whereas the other side is negatively charged, electronegative. This explains many of water's properties relative to physical and chemical reactions. It also explains why water is attracted to charged ions. Cations such as Na+, K+, and Ca2+ become hydrated because of their attraction to the negatively charged oxygen end of the water molecule. The polar nature of water also explains hydrogen bond formation by water. The bonding of each water molecule to other water molecules and to other biological components explains the solution properties. The penetration of visible light through water bodies follows a negative exponential Beer's law relationship. Rs equals RSCE. Where RSC is the solar constant and Rs is the solar radiation after passage through a depth x of water of extinction coefficient A. Since water strongly absorbs infrared radiation, that portion of the solar spectrum will be sharply depleted on penetration through water bodies. Furthermore, turbidity due to suspended solids, silt, will strongly deplete visible light. Although the prediction of visible light attenuation in pure water is relatively simple, in natural waters it is much more complex due to the variability in the nature and content of suspended materials, and therefore the simple Beer's law relationship may not be easily applied. This means that photosynthesis can occur in water, at least to certain depths. Consequently, primary producers such as plants and cyanobacteria, the basis of any food chain, can grow. Water surfaces are poor reflectors of solar radiation and therefore serve as a good sink for solar energy. However, water has a high heat capacity. The heat capacity of a substance is the amount of heat required to raise 1 cc by 1 degree Celsius. A high heat capacity means that it can absorb heat energy with only a small increase in temperature when compared with other substances. Because of this high heat capacity and the ability of water to mix and therefore to dissipate heat quickly, aquatic life forms do not have to be adaptable to a wide range of temperatures or to rapidly changing temperatures. Water becomes increasingly dense and therefore heavier at lower temperatures down to 4 degrees Celsius. This is why deeper water feels cooler in a lake. Because the maximum density of water occurs at 4 degrees Celsius, water becomes increasingly lighter at 3 degrees Celsius, 2 degrees Celsius, 1 degree Celsius and 0 degrees Celsius freezing. The density of liquid water at 0 degrees Celsius is greater than the density of frozen water at the same temperature. Thus, water is heavier as a liquid than as a solid, so that solid water and warm water can float over cold water. Figure 1. Another important consequence of these properties is that water freezes from the top down. This protects aquatic organisms because ice acts as an insulator to prevent further decreases in temperature in the remaining water and decreases the chances that ponds and lakes will freeze solid. To the meteorologist, water vapor is the single most important constituent of the atmosphere. This is because at terrestrial temperatures, water passes easily from vapor to liquid and solid phases with a large release or absorption of heat. For example, the evaporation of 1 gram of water requires about 2,430 J of heat. The D1 The properties of water 33. 1.000 minus 1 underscore 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 0.9 Q 0.9 Latent heat of vaporization. The vapor is carried in air which rises until a level is attained at which condensation occurs with its concomitant release of the 2,430 J-G1. When water freezes, about 335 grams underscore 1 is released as the heat of fusion and the same amount of energy is required to melt the snow. Sublimation, the direct transition from solid to vapor phase and vice versa without passing through an intermediate liquid phase, involves the consumption or release of 335 J-G1. Thus these energy-consuming and releasing processes in water phase changes provide the mechanisms for the transportation of large quantities of heat to and from the surface of the Earth. These processes play an important role in energy transfer and availability of energy to biological systems.